Hello there, welcome to my channel, and today we're looking at the improving language understanding by generative pre-training, the model precursor of one of the most popular models out there, GPT-3. And this is the first model they developed, GPT-1. And this video is the start of the series where we're going to cover all of the GPT models and see if the actual GPT-3 deserves the hype that it got. So here I want to present the key ideas of this paper, the datasets they used, the architecture details, the results they achieved, and also at the end review the code that I wrote for GPT, and which should solidify the knowledge you gain during the paper review and also helps you to maybe replicate the results they've got, or if you want to train it yourself. So okay, without further ado, let's jump into it. So the title itself says a lot about this paper, and the GPT acronym actually comes from Generative Pre-Training. And Generative Pre-Training is basically a self-supervised learning for NLP tasks, for natural language processing tasks. And self-supervised learning is a method that leverages the stream of data that comes with the free supervision. So if you think about it, you can actually, if you take a book which has, let's say, roughly 10,000 words, you can actually chop it into the windows of, let's say, 100 words. And based on this 100 words, you can predict the next word. And moving this window, you can actually create a lot of data set for your model. And in this method, you don't actually need to manually label this data. It's already labeled itself because of the sequence structure. So in this case, they actually pre-train it using 7,000 books. And first of all, it comes with, obviously, they are not manually labeled. But on the top of it, the model itself learns the underlying structure of the language. So it learns how to basically create the sentences. So basically, it learns the structure of the language. So it looks like this. Basically, we pass 7,000 books. This is called generative pre-training, and then we fine-tune it. So we have the labeled tasks. So in this case, we are not predicting the next word, but we predict the label of the task that we want to do. So for example, for classification tasks, we have two labels, positive or negative in the sentiment score. So this is really interesting idea. And they actually beat the state-of-the-art results on 9 of the data sets that they fine-tune on. They beat the state-of-the-art results from the models that they were explicitly train on this task. Generally, that's this is what the name comes from, generative pre-training. Most of the deep learning methods require substantial amounts of manually labeled data, which restricts the application in many domains that suffer from dearth of annotated resources. So obviously with the pre-trained models, we can actually train it on the examples that we train it on the data sets that we don't have much of a labeled data. So that's another advantage of using self-supervised learning. Second key idea that they have here is they use transformer for it. It's a bit modified decoder from the original paper. There we see had two multi-head self-attentions. We're gonna get to it soon. I just want to show you how the loss function works in a unsupervised pre-training and supervised fine-tuning. In a self-supervised training, they actually maximize the following likelihood. So based on the previous word, they try to predict the next word. So they try to maximize the probability of choosing the correct next word based on the window of the words that we got before. In supervised fine-tuning, we actually try to maximize the likelihood of predicting the correct label. So as we said before, if you want to, if you've got the classifier or sentiment classifier, so if the sentence is negative or positive, so you want to maximize the probability of choosing the correct label. But what they also did here is they mix both of them. It's called auxiliary objective, but the first function is discounted by the weight gamma. I think it's set to 0.25. This is how the decoder structure looks like. So we pass the input after text and position embedding. We got the mask multi-head attention with residual connection over there. We got layer normalization, then feed-forward function, feed-forward module with 2 linear transformation. Then we got another residual connection and layer normalization, and we got 12 layers. Okay, and at the end, as you can see here, we've got 2 heads So first head is a text prediction. So this is our first loss function where we try to predict the next word, and task classifier. So here we want to predict the correct label. Okay, so they train it on 4 different tasks. And yeah, let me show you how they look like and how the labels look like and how they pass it to the actual network. So textual entailment is the first task, and it measures the logical reasoning of the model. Okay, so we got also 3 labels: entailment, contradiction, and neutral. So entailment is when 2 sentences are, so if the hypothesis is a logical consequence of the premise. So when Adam sleeps, Adam snores. It's a logical consequence of the sleeping, right? So it's entailment. When Adam sleeps, Adam basically can't code, right? So it's a contradiction. And when Adam sleeps and Michael sings, basically they don't have any connections between them, so they're neutral. So we got 3 labels, and the model basically we pass the start token, premise, the limiter, hypothesis, and extract token. We pass it to the transformer, and it's predicting the one of these labels. So the next task is question answering. Pass the text, which is article. It also contains the question about the article, and most of these dataset I think they use it's from the school exams, and it outputs the similarity score. And I'm gonna explain to you right now what it means. So we pass this start token, and context is actual article with question. So they combine together. We got the limiter and the answer, and then we got the extract token. Obviously we pass it to the transformer, linear function at the end, and it's actually predict the score. And this score is a similarity score between the answer, like the meaning of the answer, and the meaning of the text in the questions. Then they do it for all answers, and they compute the softmax over it, and they pick the one with the highest value. The other task that they perform is semantic similarity. So basically we compare the meanings from 2 sentences. They have 2 texts, text 1 and text 2, and the label. So we got 2 labels, duplicate and not duplicate. I wrote 2 examples. What can one do after MBBS? What do I do after my MBBS? So they are, when in terms of meaning, they are the same. So they're duplicates. And this is more tricky one. Actually, this is from one of the data sets they used. How's traffic air controlled? How do you become air traffic controller? So as you can see, the model needs to learn how to find the meanings of the sentences it's analyzed. So it's obviously not duplicate. They are actually passing 2 times the same sentences, but in a reverse order, and they actually summed it up later on. And they compute and they pass it to linear, and linear outputs basically one of the labels. Okay, then we got the classification task, and there are 2 classification tasks. One of them is a sentiment classification, where we basically output is it a negative or positive sentence. So obviously I hate you is a negative, I love you is a positive. And the other one is a grammatical correctness. So if the sentence is not grammatically correct, and if it's correct, it's correct. And this is pretty straightforward. We got the start token, we got our text, and the extract token, and that's it. It just outputs the one of these labels. Okay, so that's all the tasks. What I highly recommend to do is go to the Hugging Face. I'll leave a link down below, and you can actually go through the datasets they train it on. The datasets, they list all of the datasets here. Just copy and paste them in Hugging Face, and then you can see how they actually look like and how complicated some of the questions are. And yeah, and I think it's gonna give you a bigger overview of this task that the model is trying to solve. Now we can move to actual model specifications. It follows, so yeah, as I said, the model largely follows the original transformer work, and they train 12-layer decoder only transformer. They've got 12 attention heads. They use 3072 dimensional inner states in a feed-forward module. They use Adam optimizer. They used also similar trick that was in the original paper with warm-up learning rate. They train it for 100 epochs with 64 randomly sampled examples from the mini batch, and the context space, the context window was 512 tokens. They also initialized the network with using Gaussian distribution with mean 0 and variance 0.02. Last thing, they used GELU instead of ReLU, and it's similar to SciLU actually. It's the same subset as a SciLU, but they use this constant before the argument here. So that's the only difference. And yeah, one thing more, they used learn positional embeddings, unlike the transformer, original transformer, where they used this sinus and cosinus progressions. Okay, so they fine-tuned it only for 3 epochs, which is surprising, and yeah, it's really crazy because that shows that you basically don't need to train it for long. You just need to pre-train it, and the fast fine-tuning is pretty quick one, only 3 epochs, right? And now we can move to the analysis. So they also basically show that the more layers you use in a decoder, the better performance you get. And as we can see in GPT-2 or GPT-3, obviously they increased the number of layers and complexity of the module even more, and they got even better results. And previously they trained LSTM actually, and they prove in this paper that the inductive bias of the transformer architectures helps to basically train in the self-supervised fashion. When it comes to the paper, that's pretty much it. To conclude, the key idea is to use generative pre-training, and based on this pre-training with the understanding of the language and the structure, and then fine-tune it for the separate task you want to do. It's much more efficient and better than the normal learning from scratch. And also transformers are proving that they are really good at solving those tasks. So that's the two key ideas in this paper. So now we can actually see how the code for it looks like, and probably solidify the whole knowledge we've got from this paper. Okay, so I started with importing Torch, tensor from Torch, Torch and nmath, and Torch functional. Okay, so I created the class Decoder Layer when we pass the config. So let me show you what the config is. Config contains all in this case it's a class, but mostly you can use it as a separate file where you basically define all the variables that are used in the model. So for example, vocabulary size, I put it as a 5000. It obviously depends on the data set you have. The window, the context window, in this case it's 512. Embedding size, the number of the layers we've got. P is the probability, or the dropout probability. The number of heads, inner state in the feedforward module, device, and the number of class when it comes to the fine-tuning the model. Okay, so this is the config file, and in Decoder Layer so as in the paper we've got mask multi-head self-attention, and I created this C layer where we pass the embedding size and we multiply it by 3, and then we split it into query, key, and values rather than creating three different layers for separate query, key, and value. Also, mask multi-head attention has a linear layer on the top after we concatenate all the heads. We've got the feedforward module where we got 2 linear layers followed by GELU and dropout. We've got 2 normalization layers, and I also initialized the layers in the feedforward module with the normal distribution. So yeah, that's pretty much it. We got our forward function. So first of all, I took the dimension from the input, create the mask using the trill function in a torch. Then we got our output from the C layer. Then we split it into the query, queue, and value using torch split function. We reshape it, then pass it, then we calculate the dot product between query and key, apply the mask, calculate the attention scores, with softmax and calculate the attention scores and apply dropout on the top of it. Then we calculate the dot product of the scores and values, concatenate it, apply the linear function on the top of it along with the dropout, and that's basically the masked attention output. Then we apply the add norm as it was in the transformer paper. Then again we apply the pretty much it for the decoder layer, and we just basically combine it in a GPT module where we pass the config class. So then we got the word embeddings that converts the indexes that converts the words into the vectors. Then we got the position embeddings that add this information about the position of the words. Decoders, where we pass n times decoder layer. We also got the dropout and the config file. And again, we initialize the weights in the embedding using the normal distribution. Then we got the forward function. So again, we extract the dimension of the input, and we need to create a vector with the position in order to calculate the positional encodings. We sum the word embeddings and positional embeddings together and apply dropout on the top of it. Then we pass the output to the decoder layer in a loop. So that's pretty much it. But as you remember in the paper, we've got two heads, and one head was for the generative pre-training, and the second was for fine-tuning. So they call the generative pre-training head as language modeling head. So it takes two arguments, config and GPT. It's basically only one layer on the top of the GPT, and it predicts the vector with the probability distribution over the whole vocabulary with the score for each word. So obviously we pick one with the highest score. And yeah, we basically calculate the output of a GPT, and then we apply the last layer and we got our logits. So the other one is obviously classification head, and it takes again the config and GPT. In this case we've got two layers. So one is prediction, as it was in a language modeling head, and we add the classifier, which outputs the number of classes we want to predict. So in our case I set it to 2. Obviously the number of classes depends on the task we do. Okay, so also we initialize weights with normal distribution again, and we calculate these two predictions based on the output of GPT, and we return. So that's the whole architecture. Obviously if you want to implement it, you need to add the padding masks, but yeah, it should work if you want to train it. I also link down below the GitHub repos that people actually train those models. Anyway, this code should work. Yeah, it outputs basically what we wanted. So that's it for this video. I hope you know more about GPT in general. If you're interested in this paper, I highly recommend reading it. It's one of the most straightforward, I would say, and really intuitive paper. And yeah, if you enjoyed this video, please leave a like and hit the subscribe button, and yeah, see you in the next one.